Hello everyone, I am Vikas Gundapnedi. In this presentation, I will be talking about silicon interconnect fabric. As we know that our semiconductor industry is booming day by day. Hence, to know more in detail about silicon interconnect fabric, let's get started. Let's get familiar with the flow of the presentation. In this presentation, I will tell you the history of PCBs. Also, I will take a little deeper about silicon interconnect fabric. Apart from that, I will tell you what is meant by silicon interconnect fabric and difference between silicon interconnect fabric and chip package. Then we will get into the designing principles of silicon interconnect fabric. We will also discuss the advantages and applications along with the future scope and conclusion. So here is a pictorial representation in the development of PCBs. The first PCB can be traced all the way back to the early 900s. Paul Eiler made a significant contribution in the modern electronic industry with the invention of PCB in 1936. In 1930s, the PCBs were made from bakelite and masonite. At that time, PCB were mainly used in radios and gramophones. In 1970s, the circuitry and overall size of the boards were starting to get lot smaller and hot air soldering began to use. In 20th century, flex and rigid PCBs become an affordable option and every layer interconnect production begins. So we start with our main topic. What is silicon interconnect fabric? As we know that there is a need to make some hardware systems tinier and others bigger and bigger has been driving innovations in electronics for a long time. The former can be seen in the progression from laptop to smartphones to smartwatches to hearables and other invisible electronics. The latter defines today's commercial data centers, megawatt devouring monsters that fill purpose-built warehouses all around the world. Interestingly, the same technology is limiting progress in both arenas, though for different reasons. The culprit we contend is the printed circuit board, and the solution is to get rid of it. So, some of the researchers from UCLA shows that the printed circuit board could be replaced with the same material that makes up the chips that are attached to it, which is known as silicon interconnect fabric. Silicon interconnect fabric allows bare chips to be connected directly to wiring on a separate piece of silicon. Unlike connections on a printed circuit board, the wiring between chips on the fabric is just as small as the wiring within a chip. Silicon interconnect fabric offers an added bonus. It is an excellent path toward the dissolution of relatively big, complicated, and difficult to manufacture system on chips that currently run everything from smartphones to supercomputers. In this slide, we will discuss why we are using silicon interconnect fabric. As we know that silicon has very good tensile strength and stiffness, it is somewhat brittle. Secondly, using silicon can pack dozens of servers worth of computing capability onto a dinner plate size wafer silicon. For example, it can build a computer with 40 GPUs on a single silicon wafer. Scientists from the UCLA found by testing that silicon fabric consumes less energy than 40 standard GPUs would have. Next, the manufacturing process of silicon fabric is pretty much easier and very simple to design as compared to the normal PCB. Using silicon interconnect fabric shrinks the size of the board by 70% but also reduces its weight from 20 grams to 8 grams. It is useful to communicate better as compared to the normal PCB. Due to short wire lengths of less than 500 micrometer, silicon interconnect fabric have excellent signal transfer characteristics with low channel loss and crosstalk, which is used to achieve data rates greater than 10 Gbps per link with fine interconnect pitches. It can achieve 30 times more improvement in data bandwidth and 50 times more reduction in power compared to PCB style integration. Next, we will see the difference between the PCB and chip package and silicon interconnect fabric. As we see the figure on the right side, we can see the PCB. On the top of the PCB, there is a heatsink which is used to extract heat. In the middle of the PCB, we can see the processor die that contains circuitry which is connected to the solder bumps. The limitation of the solder bumps combined with surface warpage means these solder bumps can be no less than 0.5 mm apart. In other words, you can pack no more than 400 connections per square centimeter of chip area. Recently, the semiconductor industry has tried to limit the problems of PCB by developing silicon interconnect fabric, which we can see on the left side of this slide. In this, heat sinks can be mounted on both sides of the silicon interconnect fabric, which is used to remove more heat and let processor run faster. The main thing is solder bumps can be replaced with micrometer scale copper pillars built onto the silicon substrate. So, by eliminating the PCB with silicon interconnect fabric, the chip input-output ports can be spaced 10 micrometer apart instead of 500 micrometer, which is seen in the chip package and PCB. In this slide, we can discuss about the designing of silicon interconnect fabric. For the designing of silicon interconnect fabric, we can use the fine pitch integration approach, which allows us to integrate heterogeneous diodes on a silicon-based platform. The interconnect pitches on silicon interconnect fabric are similar to the fat wire level pitches of a microelectronic chip. For fine chip interconnections, we employ a direct metal-to-metal thermal compress bonding process, which is carried out in a flip chip fashion. Thermal compression bonding allows us to scale down the interconnect pitch down to 2 to 10 micrometer as the solder extrusion is no longer a limitation. We also remove packaging of individual diodes and place the dies directly on the silicon interconnect fabric with interdiolet spacing of less than 100 micrometer. Thus, our data links can be much shorter, which is around 50 to 500 micrometer. Our substrate is rigid silicon with silicon dioxide dielectric layer, which acts as the interconnection platform for the entire system. The wiring in the dielectric layer is compatible with the mature back-end of the line technology in CMOS fabrication. The feature size of wires in back-end of the line technology can be as fine as 0.5 micrometer, which is a 20 times reduction from feature size on organic boards. Also, fine features decreases the wiring congestion, which in turn reduces the number of wiring levels required for connections. In our silicon interconnect fabric technology, up to 4 wiring levels are possible, though this is not a fundamental limit. This technology provides better chip package interaction, elimination of under bump metallurgy, and decrease in fabrication cost. We demonstrated that the continuity of 10 micrometer pitch interconnects with interdiolet spacing of 100 micrometer and alignment accuracy of less than 2 micrometer. Next, we will talk about the advantages of silicon interconnect fabric. The main advantage of silicon interconnect fabric is it is cheaper and easier to manufacture as compared to the normal PCB. The overall cost to design and manufacture an silicon interconnect fabric can be as much as 70% less than for an silicon on chip. Secondly, silicon interconnect fabric system saves space and power and cut down on the time it takes signals to reach their destinations. Mainly, it boosts the bandwidth, reduces latency, and uses less energy than a conventional system on a PCB, as you can see in the given figure. In our next slide, we can see the applications of silicon interconnect fabric. It is used in aerospace and defense industries where there is a demand for only a few hundred to a few thousand units. Secondly, it plays an important role in the computer industry. For example, it can be useful for building powerful high-performance computers that would pack dozens of servers. Apart from that, It would lead to smaller, lighter weight systems for wearables and other size-constrained gadgets. Also, it is used in automotive industry, robotic industry, military industry, healthcare industry, consumer industry, and industrial manufacturing. Next, we will discuss about the future scope of silicon interconnect fabric. Even though large progress has been made on silicon interconnect fabric integration over the past few years, the researchers point out that much remains to be done. For instance, patterning wafer-scale silicon interconnect fabric may require innovations in maskless lithography. Most lithography systems used today can make patterns only about 33 by 24 mm in size. Ultimately, we will need something that can cast a pattern onto a 300 mm diameter wafer. Next, we will need new heat sinks or other thermal dissipation strategies that take advantage of silicon's good thermal conductivity. There is also a need of having a commercially viable high-yield silicon interconnect fabric manufacturing process, and also there is a need of mechanisms to test bare chiplets as well as unpopulated silicon interconnect fabric. Next, I would hereby like to conclude this silicon interconnect fabric by telling you some of my observations. Silicon interconnect fabric are still in early phase as it requires several changes to design methodology to deliver on the promise of silicon interconnect fabrics. It will achieve popularity for its various advantages like less power and energy consumption, less space occupancy, increasing bandwidth, and reduced latency. It will also get increasingly popular as the trends towards integration with giant industries like computer and manufacturing industries due to the less complex architecture than PCB. Here are the references where you get more knowledge about the silicon interconnect fabric. Thank you.